Hello! Today we are solving problems on the topic of acceleration, and we start with a problem with a graph. The graph shows the motion of a body, and as we can see, the motion is quite variable, i.e., at one stage the velocity of the body increases, at another it remains constant, and then it decreases. The problem is to find the acceleration of the body at each of the three plots. Let's see how to do this. First, let's remember what the concept of acceleration is in general. It's the rapidity of change in the speed of the body. To determine the acceleration of an object, we need to consider how much its velocity has changed over a given time period. We can do this by calculating the difference between its initial and final velocities and dividing it by the time taken for this change to occur. Graphs are particularly helpful in visualizing this concept, as we can easily see the starting and ending velocities and the duration of the change. By applying this method, we can calculate the acceleration for various intervals. In the first interval, the acceleration is determined by the change in velocity, with the terminal velocity for this period being 10 meters per second. The initial velocity for this section is 0, and the time at which the change in velocity occurred is 5 seconds. And accordingly, we get the answer 2 meters per second squared. Moreover, the acceleration here is positive. This indicates that the speed is increasing. The movement is equal acceleration. So, the acceleration at section B, here we see the initial and final velocity are equal to each other, 10 meters per second. Respectively, the change in velocity will be equal to 0, and therefore the acceleration will also be equal to 0. So the motion is uniform. And the third plot, this plot, we see the graph has changed its angle of inclination, and in this case we see the speed begins to decrease. So the acceleration in this case will be determined by the change in speed, but with a minus sign. Let's show it. The terminal velocity for this section is 5. The initial velocity for this section is 10. The time during which the change of speed occurred is 5 seconds, i.e. from minus 15 to 20 seconds. This speed changed. And then we get the answer 5 minus 10 divided by 5. That's minus 1 meter per second squared. That's the acceleration at site C. So we can see that we can easily determine the acceleration of a body using the graph if we apply the definition of this quantity directly. We can also see with you that the angle of inclination on plot A is greater than on plot B if we are talking about a positive angle of inclination, and so we see that the acceleration on plot A is modulo 2 meters per second squared, and on plot C it is 1 meter per second squared. So we immediately look at the graph and realize where the acceleration of the body is greater. So the second problem is as follows. The car moved north with an initial speed of 18 meters per second for 7 seconds. Determine its final velocity if its acceleration was also directed northward in the first case, and determine its final velocity if its acceleration was directed southward in the second case. That is, we have two situations. In each of them, the acceleration is modulo the same, but has different directions. We need to determine the final velocity of this car. Let's write down the conditions of the problem. So the initial speed of the car in both cases is 18 meters per second. The time of movement is 7 seconds. And the acceleration is known to be 1.5 meters per second squared. Let's show in the figure what the difference is between these two situations. So we need to determine V1 and V2, which is the terminal velocity in the two cases. In the figure, let's show what the motion would look like for the first case, where the car was traveling at some initial velocity to the north. That is, we can show there that that direction is north and the acceleration is also pointing north. When the direction of acceleration matches the direction of velocity, we refer to this motion as equiaccelerated. In other words, the motion involves a continuous increase in velocity. And thus, the final velocity of the body in this case we can define as the sum of the initial velocity and the magnitude of its increase, that is, the product of acceleration over time? Well, in this case, delta t is these 7 seconds of motion, so we can immediately put a value. So, when an object moves at a speed of 18 meters per second and also accelerates by 1.5 tenths times 7, this resulting value will also be measured in meters per second due to dimensionality. So, well, the answer we get then is 20. 8.5 meters per second. That's the final velocity in the first case. Now, what happened in the second situation? The car's initial velocity is still north, keeping its direction unchanged. But the acceleration is now pointing south in the opposite direction. This indicates that when the velocity and acceleration are opposite in direction, the motion will be equally decelerated. That is, the velocity will decrease in magnitude. Therefore, to calculate this velocity, we will use the minus sign in the given formula and calculate its value. 18 minus 1.5 tends to 7, well, and the dimensionality of it will be all in meters per second. So the speed we measure is 7.5 meters per second. Therefore, the velocity is 7.5 ms, which is its terminal velocity in the second situation. In the second case, it is important to pay close attention to the sign of the received speed. For instance, if we increase the time interval from 7 seconds to 20 seconds, we may observe that the final speed could become negative. What does this indicate? It indicates that the direction of the car's motion has changed to the opposite direction. Therefore, by examining the sign of the answer, we can determine the direction in which the body is moving at a given point in time. This information proves to be very useful when analyzing the body's motion and solving problems such as determining the distance traveled or the displacement. We will delve into these topics further in our upcoming lessons. That concludes our discussion for now. Farewell.